Okay, this is make that a little bigger. This is section 4.0, theorem 4.0.10. Now, this is a nifty theorem. It's one situation where we can actually add determinants. Okay, so given, oops, I'm on a race. Given matrices A, B, and C that differ only in row I. Okay? And we'll say that with rows, and this is the important part, rows AI, BI, and CI equal the sum of the A and B rows. If that's the case, then the determinant of C is equal to the determinant of A plus the determinant of B. Okay, so if we have something like this, let's keep things relatively simple. Let's try a matrix. Let's let A equal maybe 2, 3, 1, and 0. B equals -1 and 2, 1, and 0. And so C equals 1, 5, 1, and 0. So notice only the top row is different, but the top row of C is the sum of the other two. Well, we have determinant of A is equal to -3. Determinant of B is equal to -2, and the determinant of C is equal to their sum, -5. So that's an example. They also have an example in the text. But that's pretty nice, okay? And so then that gives a corollary, right? So again, a corollary is another theorem, but it oops, I didn't spell that right. But it's usually a theorem that comes very quickly and directly from another theorem. So corollary 4.0.2, if a multiple of one row is added to another row, the value of the determinant is unchanged. Now that is something. So so the idea here is, right, that we take the multiple of another row. So we have, so I'll just kind of show similar to what they have. They did row 1, and so the basic idea of the proof is that, let's look at row 1 of C, right? C, row 1, we're going to say is equal to, say, A, row 1, plus, and something along the lines of, I guess, a T times some other row I not equal, well, I guess it could be equal to row 1, but I not equal to, yeah, so sure, it could be equal to row 1, who cares? Oh wait, no, it did say another row, so it does matter. Okay, so we had that multiple I is not equal to 1. Now, so what happens is we get that the determinant then of C is equal to the determinant of A, and then we already had our multiple of a given row, and so we can factor out that, and that's the times the determinant of AI, well, A prime, I guess, or something like that, A hat. How about A hat? There we go. So A hat, where we replaced that row of A with another row. But this has to be 0, because what we did was we simply replaced a row of A, well, this is A1, the first row, but we replaced the first row of A with some other row of A. Okay, but that meant that the new one, B, which was the replacement, it now had 2 rows the same. Okay, so that determinant had to be 0, so determinant of C is no different than the determinant of A. So again, the idea here is that we started with some matrix A, 1, 2, 3, 4, and then we made a hat by taking something like 5 times 3 and 5 times 4, a multiple of the bottom row there, and then 3, 4, and we added those two things together to get our matrix C. But so, all other rows are the same, only these rows are different, whichever ones we're doing this with, and so we get to use our theorem to do this, and so the determinant doesn't change. Okay, so that row operation didn't change anything. And let's see. So at this point, what we have is that our various row operations do certain things to a matrix, right? So let's look at our row operations. Okay, one, we could swap 2 rows. Swapping rows, changes the sign. Okay, so if I'm doing row reduction on a matrix and I swap 2 rows, the new matrix has a negative of that determinant. 2, multiplying a row by a constant multiplies the determinant by determinant of A by a constant. That same constant. And then, adding a multiple of a row to another leaves the determinant unchanged. That was our last thing. And so, in order to get a determinant, the idea is you simply row reduce a matrix down to a diagonal, sorry, not a diagonal, down to an upper triangular matrix, usually, or something along those lines to get the determinant you want. Okay, so so they give an example. Now I'm going to do their example slightly different than them. They want the determinant of 1, 2, 3, 4, 5, 6, and then 8, 8, 9, because they wanted something non-singular, I guess. Okay, so if you look at the row operations, right, we can start with that 1, and so this determinant is equal to, well, I can zero out that element and that element by taking row 4, -4 times row 1. All right, so the couple things we do are -4 times row 1 added to row 2 and placed in row 2. And we take -8 times row 1 added to row 3 and place that into row 3. Well, so when we do those two things, the determinant doesn't change. So this determinant up here is equal to 1, 2, 3. Those are both zeros. And then we get what? Let's see. So that'd be -8, that'd be -3, and -9 plus 6 is a -3, I think. Sorry, -12 plus 6 is a -6. And then we do -8, so we get -16 plus 8 is -8, and -24 plus 9 is -15. Okay, so we get that matrix. Now they then reduce things to a 2 by 2 matrix because of this 1 times the -3, -6, and so forth. Yes, we can do that. They've got zeros in the first column, so we know that those cofactors or minors are going to be 0 for all of those. But just to show at this point, then we can take the -3 out of there, right? So we can say that this is equal to -3 times the matrix 1, 2, 3, 0, 1, 2, and 0, -8, -15. Okay, so I just factored out the -3 out of one row. So you see, I just said this row was -3 times 0, -3 times 1, and -3 times 2. So then I just pulled that out. And so we have this situation. And now I can, if I want here, I can do what? Take 8 times row 2, add that to row 3 and put it in row 3. And so that will mean I'll still have that -3 out front, but I'll have 1, 2, 3, 0, 1, 2, 0, 0, and I added 8, or multiplied by 8, so that's convenient, that's a 1. And so here, though, I know the determinant of this thing is 1, because it's upper triangular, and I multiply down this diagonal, I get 1, and so this is -3 times 1, or a determinant of -3. Okay, now I didn't even have to undo that -3, it just was easier to calculate. So let me kind of go back here to this point, and we had 1, 2, 3, 0, -3, -6, 0, -8, and -15. Well, again here, what I could do is I could take 8/3 times row 2, add that to row 3, and put it into row 3. And so that would mean the determinant is unchanged, and I get 1, 2, 3, 0, -3, -6, 0, 0, and then 8/3 times the -6. Oh wait, I need a -8/3, sorry. So -8/3 times 6 is still 16, and we get a 1 here. And this determinant, though, again, that's an upper triangular matrix, so I just know that determinant's -3. So I didn't have to get all the way down to 1s. I did not have to keep reducing the size of the matrix I'm taking determinants of. I can just go through here and do my row reductions and keep track of them as I go. And I wanted to point out that difference between this and the text. So you can just do a reduced row echelon form to get the determinant, but the problem, well, let me say row echelon form, not reduced row echelon form. We can go with a row echelon form to get the determinant, but you need to keep track of things. Now, as long as all I do are these type of row operations where I add multiples of one row to another row, actually the determinant never changes, so not a problem. However, if I do decide to factor something out, like they did back here, to get to this thing, I do have to keep track of that constant when I factor it out. And I also, if I were to do a row interchange, I would need to keep track of that sign change. Okay? But that is a much more efficient way to determine a determinant. Okay, so they do a couple of examples, and I think in their second example, they do not, yeah. So in their second example, they don't reduce the matrix. They do it more like I did, and so you can kind of see their row operations moving along as they went. They do change things to ones and so forth and pull out multiples of rows, but you wouldn't actually have to if you didn't want to. And they also do a row interchange. Okay, so we'll call that good for this one.